These are two of the more difficult types of problems we did last Wednesday. So the first one here, number one, is an absolute value problem. Now, I purposely wrote it in a way that's a little confusing to us. We're used to having the variable on the left side and then numbers on the right side. So let's rearrange it that way. So 2 times the absolute value of x minus 11 over 3 plus 5. But we have to make sure we keep our symbol consistent. The 7 is the smaller of the two quantities, according to that symbol. So we make sure we adjust our symbol so that the 7 is still the smaller of the two quantities. So it's pointing at the 7. And then with these absolute value inequalities, remember, we had to basically solve it twice. We solve it the first time to isolate the absolute value, to isolate this part of it right here. And it's just like solving a standard linear equation. We're going to subtract the 5 from both sides. Now we have 2 times the absolute value of x minus 11 over 3 is greater than 2, and we'll divide by the 2. So now we've isolated that absolute value. We have the absolute value of x minus 11 over 3 is greater than 1. Once we've isolated that absolute value, we have to split this into two pieces. Remember, the first piece is just what we have here, dropping the absolute value. X minus 11 over 3 is greater than 1. The second piece, what we're doing is we're doing a -1 times the left side. So this is -1 times x minus 11 over 3 is greater than 1. And it's probably simpler for us to work with that if we divide by the -1 first. And remember, when we divide by a negative, we flip that inequality symbol. But if we multiply or divide by a negative, that inequality symbol has to flip. So now we're going to solve each of those two separate inequalities that we have. The one on the left over here, we're going to multiply by 3. So x minus 11 is greater than 3. And then we'll add the 11. We got x is greater than 14. The other one over here, same steps, just different number on the other side. So we're going to multiply by 3 to get rid of the dividing by 3 again. X minus 11 is less than -3. And then once again, we add the 11. So x is less than 8. -3 plus 11 is 8. So I asked you to give those answers both in set builder notation and in interval notation. I didn't ask for a number line, but I often find it's easier to create the other notations if I do the number line first. So here's my number line. X is greater than 14, strictly greater than. So it's either an open circle or that, that open bracket. Greater than pointing to the right. Less than 8. So there's, again, either the open circle or the open bracket pointing to the less than side, the left. So for set builder notation, that's the squiggly brackets. This is all values of x such that x is either less than 8 or x is greater than 14. Now we get asked all the time, would it be okay to do x is greater than 14 or x is less than 8? Yes, that is a correct answer. I would not mark that wrong on a test. However, there is such a thing as mathematical grammar. It's more grammatically correct if you look at the solutions on the number line. When you put them in those notations, you want to name them from left to right. It's typically more, this is the math grammar version of doing it. Then for interval notation, and again, the interval notation, it's a little bit more natural to put them left to right. Our first piece on the graph here goes from negative infinity up to 8. Negative infinity looks like this. It's less than 8, so it's not included, so it's going to be a round bracket like that, the open bracket. Then it also goes then from 14, again a round bracket because it's greater than 14. Remember, if it was greater than or equal to, it would be a square bracket, which includes the 14, but it does not include it, so use the round bracket. And greater than 14 means you go from 14 to a positive infinity, like that. Now, the one thing we did not necessarily mention on Wednesday is how do we hook these together? In set builder notation, we just use the word or. We could use the word or here, that would be fine. There's a mathematical symbol that indicates or. It looks like a big U, and that is the symbol for union. Union just means we're putting these two sets together and including everything that is in either one of them. Any questions on that one? Okay, let's go back up to the other one. I'm assuming many of you didn't even get a chance to start the second one. That's okay. So we have rational inequality here. To deal with this, the easiest way for me to deal with them is to get rid of the fractions. We have a least common denominator here, LCD, of 12. Because if denominators of 6 and 12, 12 is going to be the smallest one that both of them go into. So I'm going to multiply this whole inequality by 12. So I'm going to do 12 times the 4x minus 3 over 6. So I'm going to write it as 12 over 1 times, I'm going to put the 4x minus 3 on top in parentheses. Over 6. Now when we multiply that out, I am going to cross cancel the 6 and the 12. Both divide by 6 to give me 1 and 2. So now I've got 2 times 4x is 8x. And 2 times negative 3 is negative 6. Now the next part of my distribution here is I have 12 times 2. That's just a positive 24. My inequality symbol does not change. I multiplied by a positive 12, so I don't have to flip that. And then 12 times the 2x minus 1 over 12. Well, the 12s are just going to cross cancel there. 12 over 1 times 2x minus 1 over 12. I'm just going to cancel out the 12. That's going to give me 2x minus 1. So now it's a matter of solving that inequality. I have x's on both sides. Well, first I'm going to combine what I can on each side. On the left side, I can combine the negative 6 and the 24. So the 8x doesn't change. Negative 6 plus 24 is 18. I have 8x and 2x on opposite sides. I have to get rid of one. The smaller one is 2x, so I'm going to subtract the 2x. So we've got 6x plus 18 is greater than or equal to negative 1. Now it's just a matter of solving it. We'll subtract the 18 from each side. 6x, negative 1 minus 18 is negative 19. Now this is still greater than or equal to, even though we're dealing with negatives there, we're not multiplying or dividing by a negative, so we don't have to flip that symbol. And finally, we'll divide by the 3, or the 6, I should say. X equals, again, we divided by a positive, so we don't have to flip the symbol. So x is greater than or equal to a negative 3 1/6. So again, if I wanted to put that on a number line, (3 1/6) is somewhere in here. It is or equal to, so it's a solid dot or closed dot, or it would be the closed end bracket, either one. So then to put that in our set builder notation, this one's kind of redundant. It's just all values of x such that x is greater than or equal to negative 3 1/6. Interval notation, well, it goes from a negative 3 1/6. It's inclusive. It's greater than or equal to, so it's a square bracket up to positive infinity. And remember, infinity, we always use the round bracket because technically you can never reach infinity. Any questions on those two? Any questions on the homework from last Wednesday that you'd like me to go over? Okay, so our hopes is to slow down a little bit. I realized the first few classes we've clipped right along covering topics, just kind of some review topics. There were things that would be intermediate algebra and introductory algebra topics that we hope that you know coming into the course. But I realize many of them are things that you haven't seen for a while, and we do need some time to go over them. So today we're going to kind of hit one of those bridge topics that is one that you've seen before, but we're going to take it into a little bit more detail than you may have seen it. And we're going to talk about relations and functions. A relation is nothing more than a relationship between two sets of numbers. It's some sort of a rule or a connection between two sets of numbers. And I should just say a rule connecting two sets. It technically does not have to be numbers. Being that this is a math class, though, it's mostly going to be numbers. And there are several ways that we can express a relation. One is the one I think is probably the most common sense, is a mapping. And what a mapping does is it just takes those sets of numbers. There we go. And it physically shows you how they're connected. So I might have a set of numbers 4, -2, 7, and 0. There's my first set of numbers. I'm going to label those with a capital D, and I'm going to explain what that D means in a little bit. And I might have a second set of numbers, -5, -1, 3, and 6. I'm going to label those with R. Again, I'll explain what that R means in a little bit. And then the mapping will show that the connection between the sets in a physical way is just, let's say that 4 becomes 3. -2 goes to -5. 0 goes to -1. 7 goes to 6. There's our relation. It's mapping. It's connecting one set in this case numbers, to another set of numbers. Now the capital D up here, I said I would explain, that stands for domain. That is the numbers we start with. R stands for range. That's the numbers we end with. So anytime we start with a number in the domain, we have to end with the same number in the range. We start with 4 in the domain, we're going to end with 3 in the range. Now, it doesn't always stay that simple. We might have something like this, 5, -3, 6, to a range of 2, -5, -4, 0. And our mapping might say that 5 goes to -4, 3 goes to 2, and 3 goes to 0, and 6 goes to -5. Here, this is still a relation. We're mapping values or items from the domain into items from the range. But you'll notice in this case that -3 goes to 2 different values in the range. That relationship like that is going to be important when we distinguish between relations and functions here in a few minutes. We also have another way of expressing these relations, and that's ordered pairs. An ordered pair would look just like this. 6, 3, 2, 8, -4, 1. That's a set of ordered pairs for a relation. Now the domain here is 6, 2, and -4. Our range is the 3, 8, and 1. And of course, they do just get mapped within the ordered pairs. 6 got mapped to 3, 2 got mapped to 8, and -4 got mapped to 1. Now, ordered pairs, again, are a way we're used to seeing them. Kind of a link from ordered pairs is equations. An equation might list a relationship between variables. We might have y equals 3x minus 2. There's a relationship. Now, it's a little bit more difficult here to pick out the domain and range because it's not just lists of numbers in these sets. So looking at this, to find the domain, is there any value for x that we can't put in here? No, there's not. So the domain here, some books would list it out as just all real numbers. We're going to favor the interval notation for our domain. So our domain would just be listed as -infinity to positive infinity, all numbers. There's not a single number that we can conceive of that we cannot put in there for x. Then the range, often to work with the range, it's better to graph an equation. We're not going to graph this one here right now, but even though the domain goes from -infinity to positive infinity, it covers all numbers. Sometimes the range will not. In this case, you might recognize that as being a linear equation. It's going to look something like that, a y-intercept of -2 and a slope of 3. So that range does also go from -infinity to positive infinity. It covers all real numbers. So you saw me graph this equation. Graphing is one way to express a relationship, but it's not significant. It's just an alternative way of expressing the equation. So we consider a graph and equation to be really the same expression. The biggest thing with graphs and equations, and they both are used to express relations with infinite domains. It doesn't necessarily mean they go from negative infinity to positive infinity. It just means that every point in between is also part of it. Whereas our mappings and our ordered pairs can only express individual points. We can't express an infinite number of points with those modes of expression. So then the next important term here is a function. A function is just a special type of relation. My pen is not working well today, I apologize. So it's a relation where every come on now. Every value in the range, every value, this pen is going to upset me here, sorry. So every value in the domain goes to exactly one value in the range. So what does that mean? Looking back at what we did up here, this first mapping, every value in the domain goes to a different value in the range. That is definitely a function. This second mapping, however, 3 goes to 2 different values in the range. That's not one and only one. So this is not a function. The ordered pairs, well, we actually drew out the mapping for those ordered pairs, so that's definitely a function. We're going to talk about how to deal with graphs in just a minute. Let's look at another example of a mapping. So in this mapping, I have 7, 3, and -2 in my domain, mapping to 5 and 1 in my range. 7 maps to 5, 3 maps to 1, and -2 maps to 5. So the question here is this a function? And it's easy to look at this and say, well, 2 different numbers go to 5, not a function. But remember, the definition of a function does not say anything about the range having more than one value. It just says the values in the domain can go to 1 and only one value in the range. So yes, 7 goes to 5, 3 goes to 1, -2 goes to 5. Each value goes to exactly one value in the range. So yes, that is a function. If we looked at ordered pairs a little bit more closely, we might have 7, 3, 5, -2, 4, 1, and 5, 2. If we look at those, remember the values of our domain are the x coordinates, or the first coordinate, 7, 5, 4, and 5. There should be a red light there already. The 5 is repeated. It appears more than once. So now we have to double check. Does it get mapped to the same value each time? No, 5 gets mapped to -2 and 5 gets mapped to +2. That is not a function. So let's look at those graphs. What determines if a graph is a function or not? But remember, this is the x-axis, which is also basically our domain values. The y-axis, basically the range values. So if I have a graph of a function, a curve or whatever, could be a line, could be a curve like this, every value of the domain has to go to one and only one value of the range. So each point in here is basically an ordered pair. So that's the domain value there for that point. That's the range value for that point. So what we have to look at is, are there any domain values that get repeated? Well, how could a domain value get repeated? The only way a domain value could get repeated is if a graph doubles over on itself. Something like this. Now, this point has that domain value. This point has the same domain value. And in fact, this point has the same domain value. That one value in the domain actually goes to 3 different values in the range. So to test to see if a graph is a function, we use something called a vertical line test. And what a vertical line test is we just look at that graph and we ask ourselves, is there any place on that graph that we could draw a vertical line and it would cut through that graph more than once? So of course here it can cut through it more than once. That is not a function. We can have some pretty ugly looking graphs. Now that again is just like the open dot on the end of the number line, meaning that point is not included at that end. That's the solid dot. So if we look at this, we might ask ourselves, we look at it and say, well, that's too complicated to be a function. But if I draw a vertical line here and I drag it across the graph, there is no place where that vertical line is going to cross the graph twice. If I look at it, apparently it's going to be my day for some technical difficulties here. Okay, let's try this. So if I take that line and I slide it back and forth across my graph, I see that it only crosses it in one spot there. This spot calls into question, but remember that open circle there, that open end of the line of the curve, and that's not, the curve goes up to that point but does not include it. So it technically does not overlap at that point. So we can determine that we have these functions So let's take a look at some of the things that we can do with them. One of the first things that we encounter with functions is something called function notation. And this occurs, of course, when we're using equations. Rather than having something like y equals 3x minus 4, we're going to list it as f of x equals 3x minus 4. This means exactly the same thing as this. It's just using that function notation allows us to do two things, a couple of things. First of all, it's telling us that that's a function. Second, it allows us to do this. We might ask, what is f of 2? So when we say f of 2, notice we've replaced x here with a 2. That's asking us to do the same thing on the other side. Replace x with a 2. So instead of 3x minus 4, it's 3 times 2 minus 4. 3 times 2 is 6, minus 4 is 2. So f of 2 equals 2. Put in the value of 2 for x, the whole function equals 2. Well, that's kind of boring. Maybe a little bit more exciting is we might say, what is f of x plus 3? Well, remember the f of x is 3x minus 4. F of x plus 3 is going to be 3. We replace x with x plus 3 minus 4. And then we do our algebra to simplify this equation. So we're going to distribute the 3. 3 times x is 3x. 3 times 3 is 9. Remembering that we have the minus 4 on the end there. And we can still combine here. The 3x isn't going to change, but 9 minus 4 is 5. So f of x plus 3 equals 3x plus 5. So let's look at a graph here of a parabola. And I'm going to tell you that this vertex here is at the point -3, -5. If I ask you, first of all, is this a function? Of course, the answer would be, yeah. I can take a vertical line and I can run it across this. And there's no place that it's going to cross it more than once. That is a function. Bless you.